Hi everyone, here and there, the whole world. Mom, if you're watching me, be proud of me. So today we're going to talk about channels. Arek asked me half an hour. Oh, sorry. Arek asked me half an hour ago if I'm going to touch the basics on is there going to be anything interesting in my talk. So the answer is I'm going to touch the basics and it's going to be super interesting. So channels is when we think about channels, we think about concurrency, and this is very correct. And concurrency is actually something that brought me into Golang like 7 years ago. Just before the version 1 was released, when we were talking about the history, I took a look at Golang and was captivated basically by the capability of easily running the code on modern multiple CPUs. And if not Go routines, and same if not channels, I probably wouldn't touch it. So that's why I wanted to actually talk about it today. And I feel that we rarely actually talk on meetups about concurrency. Not sure why, because I think it's like the best feature of Golang. So let's start. At the beginning, some basics, some theory. Basically, this is from the Golang specifications. I took like two sentences. About channels. So one is saying. The very first sentence in the specification about channels is the channel provides a mechanism for concurrently executing functions to communicate by sending and receiving values of a specified element type. And the second sentence I found in the specification is that channels act as first in, first out queues, and basically the values are received in the order that I send. So what it tells us is that basically channels are thread-safe queues. We can use safely between Go routines, but they are not really only bound to Go routines. We could use channels just in a single Go routines. It probably doesn't make sense because we have a mutex there, and this was basically designed to be thread safe. But there's nothing actually special about channel that it must be used between Go routines. I haven't done. So. Channel type. We know, everyone probably knows how the channel type, how we declare channel type, but I wanted to point out that actually there is more than one channel type. Actually, channels can be bidirectional or directional. So if we take a look here, we can define a channel that we can send and receive the values of type T, but it can, and this is bidirectional channel that we are usually using. But we can also create a channel that we can only send data to, or channels that we can only receive the data from. And this is how we declare it. Obviously, creating the channel that we can only send data to, or creating the channel that we can only receive the data from wouldn't make sense. That's why usually we create bidirectional channel, and then we can simply cast into the specific directional channel. This is designed so if we have a function that only is supposed to read from the channel, we can basically just send a sending part to it, and it's safer then, so we know that that they cannot, for example, receive or they cannot send. So if we to create a new channel, we have to initialize it. We are using the well-known make function, the built-in function that takes two arguments. The first one is a type we want to communicate, and the second one is the buffer. We can omit the second one, and then by default is 0. And except for the fact that the buffer will be 0, 1, or 2, or 3, there is a big distinction between having a zero size buffer and non-zero size buffer. Basically, if we have a 0 capacity, we are saying that the channel is unbuffered. And otherwise, if there is a non-zero capacity, the channel is called is buffered. And we rarely think about it, but it's very crucial to actually see what's the difference in there. Obviously, the buffer channel, we have some kind of array bucket up inside. We can store elements, and the buffer, an unbuffered one will not have. But what's more into it? So we should take a look again from the specification. What the specification say about being unbuffered and buffered? So the unbuffered channel so for the unbuffered channel, the communication succeeds only when both a sender and receiver are ready. This is different to the buffer channel, which the specification says the buffer channel communication succeed without blocking if the buffer is not full for sending or not empty for receives. Now I want to focus more on the first sentence, which basically says that we can use the channel to synchronize two Go routines. What it means that if we have unbuffered channel and I want to send to a channel, like let's say I want to send this remote, I'm sending this remote to the channel, and I cannot just, because I have no buffer, I cannot just leave it there and go doing my own stuff. I have to actually hang out with my hand here in the remote and waiting for someone to take it. And only when someone on the other side will come over here and grab this remote from my hand, we can both continue doing our stuff. And this is different with the buffer channel, when I can just take the remote, put it on the floor, and go back doing my own stuff, and someone else can come whenever they want and pick it up and doing their own stuff. So we said the channel is a thread-safe queue. So with a thread-safe, not all the operations are thread-safe, but here is the list of the thread-safe statements we can use between Go routines without any further synchronization. So we can do sending, we can do receiving, and we can do calls to built-in cap and len functions. If you are familiar with channel, you can see that what we are missing here is the close. We cannot, close is not thread safe, which makes sense because you can only close the channel once from the sender side. So that's very good to remember. Let's see about sending. So sending, we know we are using this arrow thing that basically we are sending here the value 3 to the channel, and a few points about sending. So expressions are evaluated before communication begins. So if instead of 3 I would have a function here, the function will be evaluated first, and then we could, for example, block until we can send on the channel. This expression is blocking. If there is no one on the other side for the unbuffered channel, there's no one on the other side to actually receive it, we block it. We block until there is a room in the buffer for the buffered channel, or if there's a receiver on the other side from the unbuffered channel. 2 last points. Sending on the closed channel means panic, right? You cannot send on the closed channel. Sending on a nil channel blocks forever. And I would like to just stop a bit on this on the 2 last points, because there's a big distinction in there. Basically, do not disturb. So basically, sending on a nil channel does not panic, right? So if you, for example, think about maps, if you actually write to the nil map, it will panic. But on the channel, we can actually write to the nil channel. It will not panic, it will block forever. It's maybe something you don't want to do, because why would you block forever? But this is kind of not a bug. It's not going to crash your program. It's just going to block it. And sometimes you actually will want to use an expression when you want to send on the nil channel. And I will show you later when and why. Okay, after sending comes receiving. We have 2 options here. We can we can assign to a single value, or we can assign to the 2 values. The single value will just give you the value which was sent, and the second, if we use a 2-value assignment, we'll get a Boolean value as a second one, and it will tell us if the value was actually like a real value which was sent to the channel, or it was just a 0 value because the channel is already closed. So again, channel receiving for channel is blocking, and it blocks until there's something obviously in the channel. And as I said, if the channel is already closed, we can actually safely receive to the channel, and we'll get the 0 value here for the type and the false as a Boolean value. So it's a little bit safer here than send, because we cannot actually do any panic on the receive side, right? Kaplan. So Kaplan was on the list of the thread safe statements, and maybe not all of you actually know that we can do cap and len. So what it does, the cap basically is like with the array. Cap will be the capacity of the channel, which is basically the size of the buffer, and len will tell you how many elements are currently in the buffer, right? So if you run this, we'll basically see that capacity is 10, because we created this with the buffer channel with the size of 10, and we send a 1 item inside, and it's waiting for us to be received. And the last one is closing. So closing basically indicates that we are not going to send anything more to the channel. We can close only once. So if you try to close the channel twice, you're going to have a big panic. So let's see how, in this example, we're creating a channel of size 2. So there will be a buffer which can hold up to 2 elements. We're going to send 2 elements, 2 and 20. Then we're going to close the channel, indicating there will be no more items. And then we are going to try 5 times. We're going to try to receive from the channel, right? So a little bit more than we actually put inside. So cool. We got 10. We got 20, true, and then we just started to get zeros, right? With the Boolean false saying, oh, this is 0, you got 0, but it's actually not a real 0 that was sent. This is 0 that was generated by because the channel is closed. If we actually here, I can actually edit it, right? So also we got the panic here because I tried to show you that closing it twice generates panic. So obviously we don't want to like iterate all the time. So you might think like, okay, I can use like this Boolean value to actually stop the loop, which would be good, would be fine. But we can actually do it easier and use the for range statement. The for range statement is similar to using with the array, slice, string, and map. It basically iterates over values in the channel, and it stops once the channel is closed. This is very handy. Here we create a channel holding a time. The channel is buffered with 10. We want to fill the channel, so I'm just using a little trick here saying write to channel until the length is less than capacity, so until it's not full. Then we're closing the channel saying there will be no more data, and we are reading it back. So just take a look, we are not using any two Go routines, right? We are using this channel, obviously they're just examples, so they're not makes too much sense, but we don't need multiple Go routines to use the channels. And yeah, so we got all the 10 time values. We could actually see also how fast, for example, is inserting into the channel. We can see that actually we 1, 2, 3, 4, 5, 6. We inserted like 7 values within a single microsecond, right? So it's quite quick. You don't have to worry about that. Okay, so these are just basics. The not very interesting maybe basics about channels. Now I prepared for you like 3 programs, 3 apps that are going to use channels in completely different ways. So the first one will be counting prime numbers. So what we want to do, we want to create an application, a program, that is going to count how many prime numbers there is that are lower than number n. So our program will count prime numbers less or equal n. We are going to have one routine sending possible candidates, like numbers, to check. we are going to have multiple routines checking if these candidates are prime or not. And then we're going to have one routine collecting all the results from the workers and summing it up. We're going to use two channels. One channel will be for incoming jobs, this is here, and one channel will be for sending results from workers. So this is my image. Go routine, candidates, sending on the channel. Is prime, multiple workers checking if number is prime, receiving from the channel, and then we have one channel sending the results. Let's take a look at the code. This is just to show you that we have a function which is prime, is just checking if the number n is prime or not. This is very simple. Everyone probably wrote something like that in the past. We're just going through all the number less than square root of the number n and checking if the modulo this number is 0 or not. And the main function. So we are creating two channels. The check is a candidate. There are the numbers to check, and the results is the results from the workers saying how many prime numbers every worker found. So we create the go routine, which is going to send the numbers to be checked. I just took like up to 2 million. So I'm going to send all the numbers between 3 and 2 million. I'm only sending the odd numbers because even numbers cannot be prime, right? So a little bit of trick here. We're just sending to the channel. Once we are done sending everything, we close the channel saying no more things to check. Now we are running workers. So we define we want like, maybe actually I will, maybe not, sorry. So we define like 4 workers. For every worker we spawn go routine, which is going to receive the items from the check channel, taking the candidates, checking if the number is prime, and summing up the results, right? And once we finish, so once the channel is closed, we stop the for loop and going to announce the number of found primes into the result channel. And at the very end, we need to collect all the results from all the workers. So we iterate, we know how many workers there are. We are going to sum up the results and tell you how many prime numbers we have found, right? So if we run it, 2 millions, we found like 148,000, like almost 149,000 prime numbers in about half a second. Now, just to show you that, if we change number of workers to like 1, I have 4 CPUs on my machine. We are getting the same result, but much slower, right? Like around 4 times slower. So we created a very nice, a very easy small app that actually is using all my CPUs to calculate the prime numbers. Now, one more thing I wanted to show you is just take a look here. So this is the same program, finding the numbers. I created the candidates, the check channel. I created it buffered with the buffer size of 100. And the question is why I picked up 100 and not something else. It's kind of random, but I wanted to show you that if actually I make it unbuffered, the result is going to be the same. That's fine. This is correct. But it's going to be much slower, like almost 2 times more slower. And the question is why? Because, as I said before, the unbuffered channel is actually synchronizing things. So I have one go routine doing very simple thing, but it's just giving me the numbers, right? The candidates. This is it. So I'm generating a number, giving out to the channel, saying, oh, here is number 3. And then I cannot just leave it there and take the next number and give it again. I actually have to wait for someone to pick it up. And I have like, let's say four go routines. One of them is going to grab my hand to take the number, and only then I can go back, take the next number, and give it back. But at the time I'm actually going back, all the 3 Go routines are waiting for the next number. So I'm just picking it up, next one will take it, and so on. Once I create the buffer, actually, I can just give all the numbers to the buffer, and then all the 4 Go routines are working all the time because there's already, the number being waiting there to being picked up. So if I don't add this buffer, I'm actually, I'm limited to one CPU generating the numbers. Now you can actually, try like different numbers here, like 10. It's going to be 800 milliseconds. So it's actually hard to figure out what the good number is because it depends how fast is the worker and how fast is the producer. The larger job to be done, the lower the buffer can be, and it doesn't actually impact this issue, right? If I do like a 1000, it's not going to speed up my program. It's actually going to go into some number like half a second here. So in terms of results, it doesn't actually matter because we only write like 4. If we have 4 workers, we only write like 4 numbers. So the whole synchronization thing doesn't actually matter at all there. All right. Now let's modify our application, and I actually don't want to have a counter and how many prime numbers there are, but I actually want to see the numbers. I want to see all the prime numbers. This seems like trivial thing to change. Instead of sending the counter into the channel from each worker, I just want to send the prime numbers. And that's true. That's the kind of only change, but the issue will be, I will go back now, the issue will be here. Because when I'm collecting the results, here I exactly know how many results there are going to be in the channel. Because there will be 1 per worker. Now if I'm collecting prime numbers, actually I don't know how many results are going to be. And if you actually remember, we didn't close the result channel here. The problem here was that we were taking the numbers from the check channel, and we can only close the channel once. So the question is, who is going to close the channel results? We have 4 workers. We cannot just pick one of them, because if we said like, okay, let's worker number 0 close the channel. The problem is we cannot do that because the channel could be closed before like worker number 1 finished their job. They would write into the closed channel and we have panic. So the trouble here will be, if we don't know how many results there are, the trouble will be how to close the results channel. And this is why I introduced this example. And I'm going to show you one of possibilities how to close the channel. Basically, we're adding, in the sync package, there's a wait group. So what we are going to do is we are going to add every worker to wait group, and so this is adding, right? We're creating the worker, adding 1, and for every worker, once the worker finishes their job, they're going to say to the wait group, okay, I'm done with working. And then we're going to spawn another Go routine, which is actually monitoring the wait group and waiting for all the workers to finish. Once everyone has finished their job, we can actually close the channel primes, saying there will be no more primes for worker. So this is the safe way of closing the channel. So amending the program this way, we can now use our range loop. We can actually now use the range loop and saying for every prime we found, print it out. I'm modifying the program to just look into up to 100, so it doesn't spam me out with 2 million results. Interesting part, obviously, here when we talk about concurrency is they are not actually in order, right? Because one worker can be more lazy, slower, faster. So we have to realize that once you put this into the multiple workers, they are not going to go back to you in the same order you were sending them. But yeah, we got all the prime numbers smaller than 100. Another app. a little bit different usage of the channel is, let's try to create a semaphore. The semaphore is like a mutex, but with, you can specify a number. So basically so the idea is that you can only, for example, allow up to n numbers of Go routines doing one thing. So here we are going to create the program that is that multiple Go routines want to work on a specific task, and we only allow up to like 2 or 3 routines working on it. So it's like a non-standard way of usage of the channel, but I just wanted to show you how that you can think out of the box and using the channel this way. So here's the function, the task. So do something, right? This is a task. And this is the implementation of semaphore. So the semaphore will be a channel with a size of 2 saying I will allow up to 2 Go routines working on this task. And in order to acquire the semaphore, we are going to send, okay, so this is the empty structure, right? So we are not going to pass any meaningful values to the channel. We are just going to fill it. We're just going to operate on the fact that the channel is full or not full. So in order to acquire the semaphore, we are going to send an element to the semaphore. If it's successful, that means there was a space in the buffer, and I can work on it. And once we are done, we are going to take the value back from the channel, and here's some work, which basically means that only up to two Go routines are allowed to run this code, and all other Go routines are going to hang here waiting for their turn. And this is run the workers. We're going to run 10 workers. In the loop, they all want to do a specific task, right? So if we do run, we'll see it starting, and we'll see that here's like a task ID, the worker ID. We see like every second, because it takes like 1 second to perform the task, every second like 2 different workers were able to work on the task, right? So sometimes actually we can see things like that in the code, that people are rate limiting specific part of the code using channels. If it's a good idea or not, it's a different thing, but you can do that. So the question is now, can I do the semaphore non-blocking? Means I don't want the workers to wait here hanging until someone else finishes the task. I just want to either acquire the task, acquire the semaphore and do the task, or just tell me I couldn't acquire it because somewhere else is working on it. Yeah, so we can do it using the select. So we haven't spoke about select before, but now we can see. So the select can take multiple cases, or in this case, 1 case, and if in terms of the channel, if the channel is ready for communication, then the case will be run, right? So if I can write the element, send the element to the channel, then I will execute this part, which means, okay, putting it, and then I have acquired the semaphore, and then I will release the semaphore when I'm finished. Default part will tell me that if I couldn't actually do anything here, go into default part and return false. So very simple change, but we created like a non-blocking semaphore, which makes the function return false if I couldn't acquire the semaphore, and true if actually I work on the job. So here is a simple example. The same thing, we are 10 workers running in the loop. We try to do a task. If we did it, we just say task done. Otherwise, we say that we would block and actually we are doing something else. So if we run it, we see that like almost everyone is doing something else. But from time to time, two Go routines actually perform the job on the task. So cool. Nobody is hanging. Nobody is waiting. Everyone can do meaningful things. But actually, you know, if you want a semaphore, you can use the one implemented not on the channels, but in the maybe more correct way, using the xsync package. And the last one, the most interesting for me, almost real life, because this is something I'm running in the production, maybe a little bit more complicated, but quite similar. So we want to write a scheduler. The scheduler will be something that takes tasks or jobs on the channel and spit it out in different order according to some priority. So we are sending tasks to the channel, receive task from another channel according to some priority. So this is not like a simple first in, first out queue, which is done during a channel, but we want to add some reordering. We are going to hit just two channels, incoming and outgoing, right? So we're going to send task, we're going to have a scheduler, and we're going to receive tasks in some other order that we can define. And when for the first time, I needed actually something like that in the code, and I was thinking how to solve the problem. So I was thinking like, okay, I have two channels. One is for receiving, so I'm thinking of how to implement scheduler. I have one channel for receiving items and one for sending, right? So maybe I'll run two Go routines. One Go routine will be receiving the items and writing it to some queue. And the other one, the other Go routine will be taking from the queue and trying to write to this channel. The problems started to arise. How do I synchronize the queue? And what happens if the queue is empty? Then the one sending the items here needs to stop. And then once it stops, the Go routine here would need to wake it up once there's a new item in the scheduler. So things got complicated. I had like two screens of code, and it was buggy, it didn't work. So I just removed everything. And I was thinking maybe I can do it easier. So yes, we can do it easier using only one Go routine, and quite nicely. So let's start. This is our main function. We have two channels, incoming task and outgoing tasks. First, we run a Go routine which is going to simulate jobs for us. It's going to write 10 numbers, 10 random numbers. The numbers will be between 0 and 1000. Then we are going to run a scheduler, taking in and out the channels. And at the end, we want to collect all the numbers from the scheduler in the main function and print it out. So I'm just, I will tell you that for now, the algorithm of setting priority is the higher the number, the higher the priority. So ideally, I want to get the higher numbers, right? So if in the scheduler we have like 1, 2, 3, I want to get the 3 first, then 2, then 1, right? So we don't have scheduler yet. I'm just going to show you that it works. I'm sending random numbers. I get it back in the way I want, except for the first item. We can talk about it, why the first item is weird later, but pretty much this is what you want, right? They're random, but they're coming back to us according to some priority. Okay, so how to write the scheduler now? Let's first create some queue. This is like a helper function, helper type, which is going to keep the jobs for us. The job for us now is just an integer. So this is a priority queue, right? So you're going to add to the queue means we're just going to append to this slice and then sort it. So we always keep the integer sorted. It's not the best way of solving it. There's a much better algorithm to solve it, like using heap or some other ways, but it just keeps it simple for the sake of the example. So we're adding to the priority queue, we sort it, and we know that the largest number is at the end. So the top will return as the top element, the higher number, which is basically the last element of the queue, and the pop method will remove the last element. Very simple queue. And then, scheduler. So the scheduler will take the incoming channel that we can receive from and outgoing channel that we can send to. We have this queue that we're going to keep all the elements. And then we have a loop. The loop says that we are keep looping until there is something in the queue or we expect something more to get. So the incoming channel is not nil. So then I create the variable xout. I call it xout because the xout variable can only have two values. It's either out, the same as out, or it's nil. And it's out if there is something in the queue. So if there is something in the queue waiting to be delivered to someone, I'm going to have a non-nil value in the xout. Otherwise, if the queue is empty, I'm going to have it a nil. Now, why I want to do that? Because I'm going to use a select here. And in the select, I have two options. One option is try to send something, and the other option is try to receive something from the incoming channel. And I spoke before that you can send to a nil channel, which means it blocks forever, which means the channel is not ready for communication. And if the channel is not ready for communication, the select will never pick it up. So this is the case that we actually are sending to a nil channel, trying to send to a nil channel, but select will never, actually, it's just like, we'll ignore it. We don't have to do any ifs, anything. It's sorted out by the select. So it means that if there is something, if it's not nil, it means there is something in the queue, which means we will take it from here. Once it's sent, we remove the element from the queue. And the second case is getting the incoming elements, which basically is we read the element from the incoming channel, we take the element itself and see if it's closed or not. If the channel is not closed and the number is real, we add it to the queue. Otherwise, if the incoming channel has been closed by the sender, meaning there will be no more items to be delivered, we send the incoming channel to nil, which again, if we go back here, will just ignores the whole case here. Because the in channel is empty, you can receive from the nil channel, it will block forever, because it means the channel is not ready for communication. If the channel is not ready for communication, the case is not going to be run at all. So basically, we like switch here between the cases which we want to run. And yeah, that's it. It's very simple. It's very simple, and it works with one Go routine and not too much code, to be honest. So again, this is our code. Why the first one is different and weird, like not in the order? It's because we created like the scheduler. So this is the most probably the very first number that was generated. So we just put the number. We generate number 196. We put it into to the channel, and there's immediately someone who is receiving it. So we don't need to do any sorting, because basically this is like the maximum number at the point that someone is receiving from the channel. But because then there's some backlog going on and the workers are quite slow because I added like a time slip over there. So items are coming into the channel and then there's sorting and we get the items in the order. So interesting thing, for example, here is that if you wanted to modify, so if you think about it, we're just adding to the queue and it's unlimited, right? If the numbers are coming in, we'll just add to the queue, and it's unbounded. And what if we wanted to, for example, say that if we already have like 100 numbers in the queue, we don't want to receive them anymore. Just block the sender saying there's too much. We need to wait for some workers to do. So it's not too much you actually you have to do. You can do the same trick here. Basically, we can just put the mic out. So we can just do like X in I'll just make some tricks here. So I have a x in being so x in will be the variable which you assign the similar to x out the in channel. But if length of Q is larger than, in this case, I will do 4. Okay. If it's larger than 4, then we are actually doing a nil here. I'm doing it in one line because it's tricky to multi-line. So again, and then I need to modify here the in to x in. And again, so here if we have more than 4 elements in the queue already, we are going to set it to nil, and we will stop receiving the items. Then if we do the pop, and it will be less than 4, we'll go back here, and we'll start receiving the numbers, right? So we could, for example, let's try to run it. So it's not now clear, maybe from example, it's hard to illustrate, but you could actually see now that they are kind of like ordered, but only in the clusters, right? Because, for example, here it's like 4 numbers here, 4 numbers here, because once we started to write numbers into the queue, it said like, okay, stop, enough. I have enough of your numbers. So we started to get them back in this here, and then this. So yeah, very nice trick with the. Remember the trick about the nil channel. It will save you a lot of code. So that's it. That's it in terms of the programs I have. And for the homework for you, I wanted to make you think about other users of channels. The interesting ones will be broadcasting. So you want to send a value to the channel and receive the same value by multiple Go routines, right? How would you do this, right? So obviously you can use multiple channels and so on. But there's very nice, interesting case about waking up Go routines. Imagine that you have like one channel, and you have multiple Go routines. Every of those Go routines is waiting on the same channel. And there's nothing there. They're just hanging, blocking, waiting for something. And how can you wake up all the Go routines at the same time? Because if I just send one item, right, only one Go routine will pick it up. Is there any way, do you have any idea how I can just wake up all the Go routines, like do like a signal, like a broadcast to everyone saying, wake up people, let's do your stuff. Yeah, it's like a one-off operation, right? If I close the channel, actually all of Go routines would start receiving the value 0, and they would wake up at the same time. We cannot reuse really this later, but it would work. Another useful way of using channels is asynchronous function calls, where you can, for example, for our workers, you could send a job, and instead of waiting for a job for the worker to return immediately, you could actually send the channel within the job and saying, hey, once you figure out what the response is, once you've done the task, please send me the response to this channel, right? And you can just wait for the response somewhere else in your program. So no examples here, but I encourage you to sit down and try to figure out and use the channels this way. Yeah, thank you. If you have any questions, I'm happy to answer. Hopefully you learned something, at least one thing, from the basics about channels, and happy to help.